Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
Welcome. Today we're diving into one of the biggest debates in the history of science, the clash between Niels Bohr and Albert Einstein about what quantum mechanics really means.
A debate that went way beyond just science.
Exactly. It gets right to the core of how we understand reality itself.
Our source material is called, appropriately enough, Bohr versus Einstein, the quantum debate. And it's packed with these little snippets that really capture the intellectual fireworks between them.
To really get this, we have to go back to the early 1900s.
Yeah.
Classical physics, which was all about Newton and his laws, said the universe was like a clock.
Predictable, you know the forces, you know the starting point, you know what's going to happen.
And Einstein, he was a huge fan of that worldview.
Yeah.
So when quantum mechanics came along and said, hold on, maybe it's all about probability, he wasn't too happy.
He really believed that if we just knew enough, if we found these hidden variables, then all this uncertainty would just melt away.
But quantum mechanics, it goes in a totally different direction. The uncertainty principle, the big idea from Heisenberg, says that for some things, like knowing a particle's position and its momentum at the same time, you just can't have both with perfect accuracy.
And it's not that our tools are bad. It's like this uncertainty is baked into nature itself.
So at the heart of it all is this conflict.
Mm.
Is it all set in stone, or is chance really running the show? Let's hear it straight from the source. We'll do a dramatic reading. I'll be Einstein, you be Bohr.
Okay, let's do it.
Niels, this probability stuff, it really bothers me. I just can't accept that nature's abandoned laws for the roll of dice. I think if we had deeper knowledge, some hidden variables we haven't found yet, all these probabilities would turn into certainties.
Albert, you're holding on to an old dream. The quantum world isn't hiding details from us. Probability isn't some kind of disguise. It's the real face of how things work at that scale.
But if there aren't strict laws, how can we really claim to understand nature? Isn't that just giving up and saying we're ignorant?
Not ignorance, Albert, a new kind of understanding. We're learning that not everything is predetermined. Our equations, they predict probabilities perfectly. True understanding comes from accepting how subtle nature is, not trying to cram it into our old classical boxes.
This really gets to the core of their disagreement. Einstein wanted a universe with definite answers, so probability felt like we were missing something. He believed there was a deeper theory out there that would bring back order and predictability to the quantum world.
And Bohr was saying, no, probability is fundamental. This new framework, even though it's counterintuitive, is actually giving us a deeper, more accurate view of how nature operates.
And this goes beyond just probability. It gets into their fundamental ideas about what reality even is. Einstein was a realist through and through. He thought there was an objective reality out there that exists, whether we're observing it or not.
He's famous for saying, I like to think the moon is there even if I am not looking at it. For Einstein, it didn't matter if someone was measuring the moon or interacting with it. Its properties were just there, solid and real.
But Bohr had a way more radical idea. He said that at the quantum level, things don't have definite properties until they're measured. The act of measuring, according to Bohr, actually helps to define reality.
That's a tough one to wrap your head around. It goes against everything we usually think about how the world works.
Let's hear them battle it out again. Another dramatic reading.
I'm ready.
Niels, think about the moon. I can't believe that it only exists or has properties when I look at it. Surely nature is just there, solid and independent. It doesn't need us to look at it to become real.
At our scale, sure, the moon is stable, but an electron's position. Before we measure it, the very idea of it having a definite position might not even make sense.
You're saying that reality depends on our measurements, as if nature needs us to make it real. That's a strange and disturbing thought.
Not permission, Albert. Interaction. At the quantum level, reality and measurement, they're woven together. We have to expand our idea of what existence even means beyond our comfortable classical ideas.
This highlights the massive philosophical difference between them. Einstein, holding on to that classical objective reality, found Bohr's ideas unsettling, almost mystical.
But Bohr was arguing that quantum mechanics was showing us a new kind of reality, one where observation plays a key role.
This difference becomes super clear when you look at wave-particle duality, another bizarre thing that quantum mechanics brought up.
It's this puzzle where light and electrons, things we usually think of as either waves or particles, can actually act like both, depending on how you observe them.
Take the double-slit experiment. A single photon, a single electron. It can create an interference pattern, like a wave if you don't try to figure out which slit it went through. But put a detector there to track the particle, and the interference pattern vanishes. It's like it suddenly decides to act like a particle.
And this duality really bothered Einstein. It didn't make sense to him that something could be both a wave and a particle. In classical physics, that's a contradiction.
And Bohr's answer to that was complementarity. He said wave and particle descriptions aren't contradictory, they're just different sides of the same quantum coin.
The way you set up your experiment, the context, that determines which side you're going to see. It's like nature is changing its behavior based on how we choose to look at it.
It's as if nature is saying, you want to see a wave. Okay, here's a wave. You want to see a particle. Boom, particle. A total departure from classical physics.
Let's see how they talked about this.
Light is a wave. Light is a particle. It just doesn't make logical sense. How can something be two opposite things at once?
Not opposite, Albert. Think of it like two different languages describing the same thing. One experiment speaks the language of wave, another experiment speaks particle. Both languages are correct, but you can't speak both at the same time. The experiment you choose determines which language nature will use to answer you.
But we want a single consistent picture. A photon that's sometimes a wave and sometimes a particle doesn't tell a straightforward story.
The story is richer than our old categories, Albert. Embrace the complexity and you'll find a deeper coherence, one that respects the experimenter's choices and nature's flexibility.
They just couldn't agree. Einstein wanted a single, clear picture of reality. He couldn't reconcile this wave-particle duality with his classical way of thinking.
While Bohr was embracing the ambiguity, the context-dependent nature of quantum mechanics, to him, complementarity wasn't a flaw in the theory. It was a reflection of how strange and rich the quantum world really is.
This back and forth set the stage for what became known as the Copenhagen interpretation, which became, for a while, the main way of thinking about quantum mechanics. This interpretation, with its acceptance of probability, its focus on the role of measurement, and its ideas of complementarity and contextuality, it challenged our classical intuitions and gave us a new framework for understanding the quantum realm.
And from this point, the rise of the Copenhagen interpretation, that's where we'll dig deeper into the Bohr-Einstein debate in the next part of our deep dive. This Copenhagen interpretation, like you said, it really changed how we see reality.
It challenged classical physics right at its core and made physicists face these huge philosophical questions.
Yeah, like what does it even mean for something to be real?
One of the wildest things the Copenhagen interpretation says is that probability, it's not just that we don't know enough, it's actually built into reality itself at the quantum level.
In the classical world, if you knew everything about a system and all the laws, you could predict the future perfectly. But quantum mechanics comes in and says, nope, at the subatomic level, chance is in charge. Even if you knew everything about a quantum system, you could only predict the probabilities of different things happening.
So instead of looking for hidden variables to make it deterministic again, Bohr said we have to accept probability as part of the quantum world.
Exactly. And this leads to another big idea in the Copenhagen interpretation. Measurement actually does something. In classical physics, you just observe something, you don't affect it. But in the quantum world, the act of measuring actually helps to shape reality.
That's where wave function collapse comes in, right?
Yeah. Right. Before you measure it, a quantum system is in a superposition of states. It's like, think of a coin spinning in the air. It's not heads or tails until it lands and you see it. Same with a quantum particle. It doesn't have a definite position, momentum, or spin until you measure it.
So when you measure it, you force it to choose one definite state out of all the possibilities in the wave function. That's the collapse.
Exactly. And which state it collapses into. It's not predetermined. It's all about probabilities, the ones set by the wave function itself.
So even if you knew everything about the system beforehand, you still couldn't say for sure what would happen when you measured it.
And again, this uncertainty, it's not because our instruments are bad or we don't know enough. It's just how nature is at that level.
The Copenhagen interpretation also says that our everyday language, the words we use, they don't really work well to describe the quantum world. Words like position and momentum, which are clear in classical physics, get all fuzzy and context-dependent at the quantum level.
Bohr said we shouldn't try to force quantum stuff into these old classical categories. We have to accept that some properties, like position and momentum, they only really have meaning when you define the specific measurement you're making.
And that's where complementarity comes in, right?
Yeah.
Bohr said some pairs of properties like position and momentum, you can measure one accurately or the other accurately, but never both at the same time.
It's like they're mutually exclusive, but also both necessary to describe a quantum object fully.
So it's not that the theory is flawed, it's just that the quantum world is inherently ambiguous and context dependent.
And this whole Copenhagen interpretation, with its radical ideas about probability, measurement, and complementarity, it really clashed with Einstein's deep beliefs about how the universe should work. He just couldn't accept a reality that was fundamentally probabilistic and dependent on the observer.
Yeah, let's hear them go at it again. Another dramatic reading from the source material. What do you say?
Let's do it. Bring on the quantum drama.
Niels, this Copenhagen view, it puts measurement right at the center of reality. It's like we've given up on trying to describe what exists on its own. Is this really science anymore?
We've discovered a realm, Albert, where the idea of properties existing independently just doesn't hold up. The quantum formalism, that's our guide, and it shows us that what we call properties, they depend on how we measure them.
But that makes reality subjective. Are we turning into philosophers now? Abandoning the objectivity that's always been at the heart of science?
It's both, Albert. At this scale, physics and philosophy, they're meeting. Our theory is a map of how we interact with nature, not a photograph of some hidden world that's completely separate from us.
You can really hear the philosophical divide between them. Einstein, with his focus on scientific realism, he just had to believe that there's a description of reality that exists independently of us looking at it.
And Bohr is saying, no, quantum mechanics is making us rethink what it even means for something to be real.
Einstein, even though he admitted quantum mechanics worked in its predictions, he never fully accepted the Copenhagen interpretation. He thought it had to be incomplete, that there had to be a deeper level of reality that would bring back determinism and a more classical view.
And that's what led him to come up with, along with his colleagues Podolsky and Rosen, a thought experiment that became known as the EPR paradox. It was a brilliant attempt to show what he saw as the fundamental flaw in quantum mechanics, this apparent violation of locality.
The EPR paradox. Imagine two entangled particles, they interact, then fly off in opposite directions. Quantum mechanics says no matter how far apart they get, their properties are still linked. Measure the spin of one, let's say it's spin up, and instantly you know the other one, even if it's light years away, has to have the opposite spin down.
This instant correlation across huge distances, Einstein said, it violated special relativity, which says nothing can travel faster than light.
It was as if quantum mechanics was implying some spooky action at a distance, some mysterious connection that ignored the limits of space and time.
And Einstein thought this non-locality meant quantum mechanics was incomplete. He believed there had to be hidden variables, some deeper mechanism we hadn't found yet, that would explain this correlation without needing faster-than-light signals.
Let's hear them clash again. One more dramatic reading to capture their different perspectives.
All right, back into the quantum ring we go.
Niels, this entanglement is really troubling. If there aren't hidden variables, how can we avoid saying that measuring one particle instantly affects the other one, even across vast distances? That would completely shatter how we understand cause and effect, and the speed of light is a limit.
Effect is a word loaded with our classical baggage, Albert. Entanglement shows us something profound. These particles, even though they're far apart, they're part of a single, whole quantum thing. There's no faster-than-light signal, just a correlation reflecting their shared origin, their connected nature.
Holistic correlation? That sounds more like mysticism than science. I was looking for a simpler, more rational order, one governed by local interactions and clear cause and effect.
The universe, at its deepest level, Albert, it's not bound by our desire for simplicity or our classical intuitions. It's richer and more subtle than we could have ever imagined. The old categories of local realism just can't handle quantum interconnectedness.
So despite his strong feelings about entanglement, Einstein never figured out how to reconcile it with his belief in local realism.
And this clash, their struggle to understand what entanglement means, it became a central theme in their ongoing debate. It shaped their discussions at the Solvay Conferences, those legendary meetings where the greatest minds in physics came together to tackle the fundamental questions about reality.
Those conferences were more than just academic gatherings. They were intellectual battlegrounds. Einstein, convinced there had to be a more complete deterministic picture, would challenge Bohr and the Copenhagen interpretation with these ingenious thought experiments.
And Bohr, with his deep understanding of quantum mechanics and his willingness to embrace its counterintuitive implications, would carefully pick apart Einstein's challenges, showing again and again that there weren't any inconsistencies as long as you took all the quantum principles into account.
Let's imagine one of these exchanges. Back to the heated atmosphere of the Solvay Conference, another dramatic reading.
Okay, the debate rages on.
Niels, I have a new scenario for you. Imagine a photon trapped in a box. If we measure the box's mass before and after the photon escapes, we can figure out the photon's energy very precisely. And if we time the escape accurately, we know the time of emission very precisely too. Doesn't this contradict the uncertainty principle, which says we can't know both energy and time with perfect accuracy?
Your thought experiment is clever, Albert, but you're missing something. When you factor in gravity's effect on the measuring device itself and insight from your own theory of relativity, we find that the uncertainty principle still holds. The very act of measuring the box's mass to determine the photon's energy introduces an unavoidable uncertainty in the time measurement.
Ingenious. You always have a subtle way of escaping my traps. But maybe this shows that quantum mechanics is just too slippery to be captured by classical logic.
Not slippery, Albert, just honest about nature's complexity. Your tests assume that classical logic still works, but it breaks down in the quantum realm. Quantum theory thrives where classical logic fails. It embraces uncertainty and complementarity as fundamental parts of reality.
These exchanges at Solvay, even though they never fully resolved their differences, they were incredibly productive for quantum mechanics.
They forced everyone in physics to really confront what the theory meant and to sharpen their understanding of its core principles.
And even though Einstein never fully accepted the Copenhagen interpretation, his constant challenges and thought experiments actually helped make it the dominant view, at least for a while.
But the story doesn't end there. This debate that Bohr and Einstein started, their struggle to understand reality in light of quantum mechanics, it echoed for decades, inspiring new interpretations and leading to revolutionary experiments that would further challenge our classical way of thinking.
The debate didn't end when Bohr and Einstein passed away.
It kind of kicked off a whole new chapter in physics, moving from thought experiments to actually testing these ideas in the lab.
Decades after those epic showdowns at the Solvay Conferences, a physicist named John Bell came up with this theorem. It was a way to actually experimentally see if Einstein's idea of a local deterministic universe was right, or if the non-local probabilistic world of quantum mechanics was the real deal.
Bell's theorem, it was published in 1964, and it was huge. It showed that any theory relying on local hidden variables, which was Einstein's thing, would have to make different predictions than standard quantum mechanics.
So Bell's theorem gave us a roadmap for an experiment to settle this decades-long debate. It was a way to test the very core of quantum mechanics and see if Einstein's hope for a more classical explanation could hold up.
Exactly. And starting in the 70s, these groundbreaking experiments culminating in Elaine Aspect's work in the 80s, they put Bell's theorem to the test. It was cutting-edge stuff, pushing the limits of precision and quantum control.
So what happened? Did the experiments prove Einstein right? Or did they confirm how strange the quantum world really is?
The results were crystal clear. They backed up quantum mechanics, completely violating Bell's inequalities and ruling out a whole bunch of those local hidden variable theories.
So those experiments basically shattered Einstein's dream of a classical deterministic basis for quantum mechanics.
Yeah, and those experiments and tons more since then have shown without a doubt that non-locality is just a fact of life in the quantum world. Entangled particles, even when they're super far apart, they have this connection that you can't explain with any local classical mechanism.
So even though we can't use it to communicate faster than light, this non-locality, it really messes with our ideas about space-time and how information can travel between things. It suggests this deep interconnectedness that just doesn't fit with our classical view of cause and effect.
For sure. And even though the Copenhagen interpretation is still a big deal, the whole Bohr-Einstein debate, it's still inspiring new ways to understand and interpret quantum mechanics and what it means for reality.
So even though experiments have ruled out local hidden variables, physicists are still trying to figure out different ways to make sense of quantum mechanics and how it affects our understanding of reality.
Exactly. Like the many worlds interpretation, for example. It says that every time you make a quantum measurement, the universe splits into a bunch of branches. Each possible outcome happens in a different branch.
So instead of one reality where wave functions collapse, the many worlds interpretation says there's a whole multiverse where every possibility exists all at once. Talk about a mind-blowing idea.
Totally. Another one called Bohmian mechanics. It brings in non-local hidden variables to make it deterministic again. But you got to give up the idea of locality to make it work.
It seems like no matter how you slice it, quantum mechanics always throws these counterintuitive concepts at us that challenge our classical view of the world.
And that's the real lasting impact of the Bohr-Einstein debate. It pushed us to understand reality in a whole new way, forcing us to see the limits of our classical intuitions and to embrace just how strange the quantum world is.
So where does that leave us? Are we in a universe where chance is fundamental and measurement shapes reality? Or are there deeper layers of order we just haven't found yet? Is the moon really there when we're not looking, or does it just become a fuzzy cloud of quantum possibilities?
These are questions that are still driving research in quantum foundations. That debate that Bohr and Einstein started, it's still inspiring us, guiding physicists, philosophers, mathematicians as they try to crack the deepest mysteries of the quantum realm.
So we've come to the end of our deep dive into the Bohr-Einstein debate.
Yeah.
But the questions they raised, they're still just as relevant and mind-bending as they were back then. It's amazing how a debate that started almost a century ago is still shaping the cutting edge of science today.
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.